Hey everyone, welcome back. This week we're going to be focusing on forests. This presentation is specific to temperate forests, although there's some YouTube videos on the Canvas module page about tropical forests, and much of the disturbances in temperate forests are similar for tropical forests too. So we'll go over a quick introduction. We'll talk about disturbances in temperate forests, both small scale and large scale. Again, these are pretty similar in tropical forests also, and then talk about stand development, recovery following disturbance. This map is showing us the distribution of temperate forests in green here. You can see other major biomes in different shades of gray, but focusing on the green, you can see just the distribution mostly in the northern hemisphere. Again, we're talking about temperate forests. If instead we were looking at a map of tropical forests, you would imagine that that green would show up in between the Tropic of Capricorn and the Tropic of Cancer in the tropics. But temperate forests mostly in the northern hemisphere, although those little land areas in the southern hemisphere, South America, Africa, and Australia as well. And although these colors are tricky to tell them apart, we can contrast that previous map with this one showing current versus original distribution of maps, both temperate and tropical forests on this map. And we can recognize, if you can parse out those colors, we can recognize there's been major disturbances and land conversion to temperate forests. Although we've lost lots of tropical forests, particularly in Africa and Southeast Asia, temperate forests have definitely gone away and been heavily disturbed due to human activity. Most of Europe used to be temperate forest, but of course now we associate it more with farmland and cities. So now we'll transition into talking about the disturbances common in these forested systems, and we'll talk about both small scale and large scale disturbances. And small scale disturbances, primarily we're talking about gap dynamics. So in old growth forests, gaps account for at least 18% of the ground area. So gaps, as they sound and as this picture shows, are just gaps in the forest canopy that let more light in than other places within the canopy. Another 60% of the forest area is at least close to a gap. So although we can think of some old growth forests as really dense and shaded, this is telling us about 78% of forested area is within or at least near a gap. So then the question is, how do these gaps get made? Trees fall over, but it's important to understand why they fall over. What's the mechanism there? And a major source of these gaps in mature forests is fungus associated with heart rot. These falling trees cause bole injuries, like injuries to the outside of adjacent trees, and those injuries are then colonized by decay fungi. This heart rot fungi then attack xylem cells, non-living cells, that are vital structural support to large trees. They help hold the trees up. So as those rot away, the tree gets weaker and weaker. And people who work in forests, foresters, have long recognized that temperate forests have what's called a pathological rotation age, or a return interval of these pathogens. So for example, in coastal western hemlocks, it's been estimated between 225 to 275 years, whereas interior western hemlock is more like 100 to 120 years. Heart rot fungi are predominantly to blame, but often we can find root pathogens in trees that have blown over also. So roots, of course, hold the trees within the ground, and if those roots become unstable because of pathogens, if they become weak, that tree is more susceptible to be blown over also. Here we see an example of a Doug fir that's been blown over by the wind in British Columbia because its roots were weakened by laminated root rot. And maybe less important, but still important nonetheless in some areas, other causes of gaps can be lightning, human harvesting, certainly, and then anything that you can imagine that would make a tree fall over itself is creating a gap. In contrast to the small scale disturbances, those gap dynamics, now let's think about large scale disturbances, these stand replacing events where most of the dominant trees are removed. We can see this image here that shows kind of this intermixed grassland to forest, although it used to be entirely forest. And remember this map, this distribution map of temperate forests across the mostly northern hemisphere. Now, the temperate forest biome is one of the most altered biomes on the planet. So you can look at this map and you'll see that human population density really closely corresponds to the distribution of temperate forests, maybe the eastern United States or all of Europe. We use the wood of these trees for construction, firewood, art. They've been cleared for farming and to build communities. And these human activities have led to the decline and loss of these forests in many parts of the world. Now, we could think about wind as the cause of small gap dynamics, also gap disturbances, blowing one or two trees down, but they're also a cause of major stand replacing events also. These can be large scale events and often are synergistic. Remember, disturbances can be synergistic with other disturbance type. So if you have more wind damage, that also provides more opportunity for pathogens or fire or insects. Wind disturbances create lots of diverse microsites. And wind disturbances, these stand replacing events, similar to fires, have return intervals for different forest types. So the return interval in the northeast of the US is about 800 years for a forest to get completely blown down, which is actually about the same as a major fire in that same forest type. For example, more locally, a windstorm in Colorado in 1939 was responsible for an outbreak of spruce bark beetles and blue stain fungus that resulted in a loss of canopy dominance over 300,000 hectares. Insects can also be a cause of major stand replacing disturbances. Certainly, insects have been in the news with the pine bark beetle in Colorado. Insects are always present in low to moderate levels, but they can have huge impacts on trees. Now, healthy trees are mostly able to withstand insect outbreaks. They can push the insects out and are fairly resistant to them, which is why insect outbreaks are also often synergistic. Those large landscape scale outbreaks are generally associated with a decline in tree health due to drought or wind damage or other things that have impacted the trees already, making them more susceptible to those insect invasions. And disease, of course, can also lead to the mass decline in particular species. They're similar to insects in that they're always present. Disease is always present on the landscape. But they only show large outbreaks with, again, synergistic effects when trees are already stressed because of drought or because of insects themselves or other things. Some examples of introduced pathogens include chestnut blight. If you are family or are from the eastern United States, you might know the story of the American chestnut. Now, this is an old picture, but you can see these ginormous trees with this person standing between two of them. The eastern forest used to be dominated by American chestnut. And now if you drive across the eastern United States, it's hard to find a chestnut anywhere. Most of them, if there are any, are these tiny shrub things. So there's been a complete structural shift in eastern United States because of an introduced disease called the chestnut blight that led to the death of every single one of these large American chestnut individuals. And what we think of generally, certainly in Colorado, as one of the primary major disturbances, stand replacing disturbances in these temperate forests, is fire. This is one of the most pervasive major disturbances in temperate forests, and certainly one that's linked to human activities. This table, although a little grainy, hard to see, the big takeaway is just that different forests have different return intervals for fire. So this shows pine forests in southeastern United States have fairly quick return intervals between 2 and 25 years. And you can contrast that with spruce hemlock forest in eastern Canada that has a return interval from 200 to 1,000 years. So it's highly dependent on local conditions and on forest type what the fire return interval for a particular area would be. And we can separate the fire regimes into the aspects of the canopy and the forest community that they impact. So Here we're looking at understory fires. So the understory fire regime, these are fires that really are non-lethal to the dominant vegetation, the existing trees or the larger, well-established trees, and really don't substantially change the structure of those dominant trees. Approximately 80% or more of the above ground dominant vegetation has to survive a fire for it to be classified as an understory fire. And some forest types that really rely on rapid turnover of understory fires include giant sequoia or western white oak forest, intermountain and west coast ponderosa pine, redwood, longleaf slash pine, oak hickory. It's well established that when these understory fires don't happen very frequently, the fuel loads build up, and those baby trees grow up, and generally those forests become more dense than they should be. And that's in contrast to a stand replacing fire regime. This is where fires kill the above ground parts of the dominant vegetation, those established trees, and of course they therefore change the above ground structure pretty substantially. For something to be a stand replacing fire, it has to approximately lead to 80% or more of the above ground dominant vegetation dying due to the result of that fire. Some forest types that rely on stand replacing fires include coastal subalpine trees, coastal Doug firs, hemlock Sitka spruce, lodgepole pine, western white pine cedar, western larch, or even oak gum cypress if you're from the southeast. Now, a lot of these forest types actually have what's called serotinous cones, which mean, like lodgepole pine is a common example of a serotinous tree. That means that the cones and the seeds within those cones don't actually open up and become available to germinate unless a fire comes through and the heat actually opens up those cones. And hopefully, based on historical evolution and the natural history of that species, that seed will find its way into recently exposed soil. All that light following that fire provides really great opportunity for recruitment of new young individuals. And some trees actually have what's called a mixed fire regime. So this is where the severity of fire either causes select mortality of some dominant veg, depending on the different trees' susceptibility to fire, or it just varies between the understory and stand replacement across years or across space. Some examples of this include Doug fir, lodgepole pine still, pinyon juniper, ponderosa pine in particular areas of its range, east of the Continental Divide specifically, aspen, whitebark pine, loblolly shortleaf pine, and beech maple. Now we can shift to anthropogenic disturbances in forests. Certainly, we just talked about fire, and fire is associated with human activity, so both naturally occurring event, but also anthropogenically caused. But entirely anthropogenically caused is harvesting. In the eastern United States, 96% of forests have been harvested. 96%. This is for fuel or for building material and also for conversion to agriculture. In the western United States, luckily, some larger areas of old growth have been retained. And actually, the extent of temperate forests has increased recently in many regions. So this graph shows the percent of change current to 1980 forest area. And Europe has seen a 4.1% increase. North America, 2.6%, Australia, Japan, and New Zealand, 1%. Generally, the developed world has seen an increase of 2.7% in temperate forests. Whereas other parts of the world, the developing Asia and oceanic areas, Africa, Latin America, and then generally just the developing world taken as a whole, has seen a decrease of about 9.1% in temperate forests. And harvesting can be highly variable. This disturbance from harvesting can span the spectrum from fairly small-scale minor impacts to completely stand-replacing events. Currently, most remaining managed temperate forests are managed with the hope and the expectation of mimicking the disturbance regime that initiated the stand, or that forest type and that forest stand has evolved to respond to. This includes a reduction or loss of canopies, how nutrients are removed from the system, and making sure that there's high resource availability for that subsequent sear. Harvesting, of course, is unique from other disturbances, though, in that it removes that large amount of wood. This results in soil compaction and has artificially well-defined boundaries. So now let's move into thinking about how these forests actually recover from disturbances. We'll use one model that is pretty commonly used, four-step model. And here we're looking first. Let's think that this big stand replacing event came through, maybe a big fire. And so this first stage in recovery is called the stand initiation stage. And here we're looking at a picture of a managed forest. This might involve planting, but the natural analog to this would just be a natural recruitment event, natural regeneration from seeds that are on site. An example of this would be a big fire comes through a stand of lodgepole pine, and those serotinous cones open up. There's a bunch of seeds laying around everywhere, which germinate and start growing. And so then you have this big carpet of baby trees, and this is the stand initiation stage. And with time, further recruitment of trees is unlikely. The further germination of seeds that didn't germinate already is probably not going to happen. And competitive exclusion starts to kick in. So in that first stage, the initiation stage, you had lots and lots of baby trees, but only the most healthy and the tallest end up surviving, and the weaker trees end up dying out. And so you have a slow takeover of the dominant healthy trees, and we call this the stem exclusion stage. Management is often done in this stage to promote thinning or spacing out the trees to control the species composition and form and the growth rate of trees so that the trees can grow exactly how we want them to grow if it's a very managed system. Now, the third of four stages is called the understory reinitiation stage. Just as its name sounds, we're looking at changes to the understory at this point. So the trees, the existing trees that have grown on site, they have grown through that initiation stage and the stem exclusion stage. Now they're big, established trees, and some of them start to die, and some of them start to fall down. And so these gaps start forming, or we as managers might create them, and then new trees are recruited. This increases diversity in canopy structure. So we have really tall trees, we have some medium trees, and then we have some small trees. It increases the species diversity and that spatial heterogeneity within the forest. Managed forests are often harvested at this stage. So rather than going to that fourth stage, managers will often gear towards this stage, at which point they'll cut the trees for lumber or whatever the utility is. But if the forest isn't a managed forest, then in time, it'll hit this fourth and final stage, which is the old growth stage. An old growth forest has been around for a long time without a stand replacing event. Large gaps are created, and it has this rich mosaic of age classes where you have really old trees, some really new trees, and then a whole range of trees in between. And this is probably the most complex of forests and one of the hardest forests really to find because the old growth stage takes so long to develop.